And we are live. So everybody who is currently arriving will be starting at pretty much exactly 5 past. So take your assigned seats. Hope you're excited.
Yes, strap in. Observe yourself, or not, as the case may be. Do you want to hear a bad quantum mechanics joke?
I would like nothing more.
Please share one.
Please.
Yeah, I took my car to a quantum mechanic and wasn't sure if there was anything wrong with it, but as soon as he looked at it, there was.
Everybody who is will be starting at pretty much exactly 5.
Anyway.
Oh, has anyone got the live stream running in the background?
Yes.
Upstairs. Yep.
There's the typical 20-second feedback from Zoom.
Where's the feedback coming from?
I don't think it's playing out loud for me because I'm the one streaming, but I'll double check.
Joseph Cross fesses up, it was him.
Oh, okay. That's no problem, Joe. I was just really worried that we just weren't going to be able to figure out where it came from.
Particularly once you get the loop going that you just get every 20 seconds the same thing.
Has anybody else got any quantum physics jokes? If anyone wants to put any in the chat, I can read them out as well.
It's not quite a joke, but when I was in grad school, one of our profs, Raymond Laflamme, was famous for cracking quantum jokes, to the point where grad students, we had a running joke that we turned it into a drinking game. Every time he made a quantum joke during one of his talks, we just take a shot, and then we figured that would be possibly a crime against humanity.
You just get every 20 seconds the same thing.
But we still got it somewhere, guys.
It's still going.
Lee, you can mute everybody if you're host or co-host.
I can, but then I'm worried if it's one of us. Once we get started, it will carry on.
Right. Well, I mean, you can see the people who are unmuted. There's not so many, right?
I think somebody needs to unmute sometime.
Oh, yeah, I'm sorry. I didn't realize I was muted. I was just saying to all the new people that have turned up on the YouTube, hi, we're going to be starting at 5 past.
I don't know where this is coming from, guys. You can unmute yourselves. I muted everybody.
I mean, all of us, the people speaking should unmute again, because obviously we will have to unmute.
Yeah.
It's not a feedback between us, it's some individual thing, so we can figure out which one it is. I think somebody needs to unmute sometime.
Oh, yeah, I'm sorry. I didn't realize I was muted. I was just saying to all the new people that have turned up on the YouTube, hi, we're going to be
Sounds like it is one of us, really, because...
yeah, it must be.
All right.
Guys, you can unmute yourselves. I muted everybody.
Funny.
quite a long persistence time, this.
If you're not wearing headphones, I can always suggest that you do.
Oh, that's not a bad shout. Okay.
I think you can, in the YouTube video, there's a speaker symbol on the player, right? You can just turn that off.
Yep. Or you can also, if you think it's one of your tabs, you can right click on the tab and you can say mute window.
Right, you can do that.
And it will just mute that one.
Yeah, I don't have it on, so hopefully we've sorted it. Cool. It's 5 past. Are we ready to go?
Yeah.
Yeah.
So I will do my little introduction. So hi everyone. I'm Holly and I'm the president of the Physics Society. Thank you so much for coming. We have people on Zoom and people on YouTube, and we are so happy that you're all here. If you're part of the Zoom call but you are not one of our speakers, can I ask that you turn off your camera and microphone just to keep things as like neat as possible. Yeah. This is our first ever quantum physics panel, which is very cool. And my committee and I have been working really hard to make this event amazing. So I really hope you enjoy it. So I'm going to pass you on to my colleague, friend, and the secretary of the Physics Society, Joseph Cross, to tell you a little bit about the event.
Hi, I'm Joe, and we're obviously here for the inaugural quantum mechanics panel. So quantum mechanics, whilst widely known, is often seen as something of an esoteric subject, especially the concern of physicists, and its significance. Whilst it's appreciated intellectually, most people don't really know what the outreach of this is in numerous other disciplines and what the impact is in your everyday experience. So we hope with this dialogue that we will be presenting this fascinating discipline from several perspectives to stimulate new ideas and interpretations both in academia, and also hopefully open this discipline, which is widely considered inaccessible, to you, and perhaps inspire you to find out a little bit more about it.
And without further ado, let me introduce you to our chairs for the evening. We have Dr. Sam Carr and Dr. Gunnar Muller to tell you a little bit about quantum.
Okay, thanks, Holly, and Joe and PhysSoc for putting on this fantastic event, and I'm delighted to be here. So what is quantum mechanics? What can you do with it? And why should you care? Well, these are 3 of the things we're hopefully going to be informing you of this evening. And to do that, welcome to this multidisciplinary panel, that we have more than just physics here. We've decided basically the people we could drag down to us from maths, from philosophy, and from computing, and we're going to get the perspective of all of them on quantum mechanics and have a dialogue, a discussion, which will hopefully be entertaining and enlightening in equal measure. So over to Gunnar.
Yes, thanks for the quick introduction of the event. And so the way this will all unfold is we have 4 panelists, and we'll start by having a 15-minute presentation from each of them. And our idea is that we let them speak while they're at it. However, we very much expect that you will, of course, have questions. So please, meanwhile, post those questions in the chat, either on Zoom or on the YouTube page. And we will then collect the questions and feed them back into the discussion towards the end. So after the panelists have introduced their topics from the point of view of physics, for Paul Strange, mathematics for Claire Dunning, computing for Carlos Perez Delgado, and philosophy from Graham Forbes. So after all that, we're going into a more open discussion around some topics, and then finally we come to your questions as a panel. And please remember, do post your questions throughout. With that, I think it's up to Sam to introduce our first speaker.
Well, I wasn't going to introduce the speakers, I was going to let them introduce ourselves. So let's actually just go round each of the speakers, starting with Paul. So could you just please state who you are and also what's your favorite thing about quantum mechanics? You're muted, Paul.
You have your mute button on. Oh, Aston. Okay, good.
I'm Paul Strange. I'm Emeritus Professor of Theoretical Physics at the University of Kent. The thing I like about quantum mechanics most is that I've been working in it for getting on for 40 years now, and it still has the power to surprise me. In fact, in my research, in fact, that happened to me yesterday. I got a result that really shocked me. So it's still surprising. It's so deep and puzzling that it's still surprising after 40 years. That's my answer to that question.
Okay. Thanks. Claire.
Good evening, everybody. My name's Claire. I'm from the Maths Department at the University of Kent. I teach quantum mechanics at the moment, and the thing that I like about it is we don't have all the answers. We very much don't have all the answers.
Okay, Carlos.
Hello, everyone. Thank you for the invitation. My name is Carlos Perez Delgado. I'm a lecturer in the School of Computing, where this term I'm actually teaching a course, an introductory course to quantum computing and quantum cryptography. And my favorite part about quantum mechanics is definitely the jokes.
Okay, Graham.
Hi, I'm Graham Forbes. I'm a metaphysician in the philosophy department, and by far the least qualified to talk about quantum physics here. But the thing I like most about it is that it really challenges our understanding of things that we thought were really well understood, like what a thing is. I mean, the word thing is about as basic as you would thought you would get, and it's going to turn out like, hey, we don't even know what things are.
Cool. And finally, Nigel. You're muted, Nigel.
Sorry, I'm Nigel Mason. I'm in the Physical Sciences Department here at Kent. I started my career as an atomic and molecular physicist, and therefore looking at things on the atomic scale, looking at electrons' interaction with atoms from the very small. But today I work more in the space side of things, which is the very large. And what I find fascinating about quantum mechanics is that it's relevant to the very small, and it's also relevant to the very big.
Fantastic. So this is our panel. I look forward to hearing much more from them throughout the course of the evening, but without further ado, let's just get started on the presentations. And the first will be from Paul Strange on physics and quantum mechanics.
Okay, thank you. Thank you. I'd like to thank the organisers for inviting me to give this talk. I was initially a bit reluctant to give it because quantum mechanics is such a vast and deep subject. I just felt inadequate to the task, but I work in a research group called the Physics of Quantum Matter. And when quantum's your middle name, it becomes a bit difficult to maintain a position that you don't know enough quantum mechanics. So I agreed to give it. Nobody is born with a fully formed view of what quantum mechanics is, and you're influenced by a lot of people. The principal influences on me are listed on the at the bottom of that transparency, and I'd like to thank them. And if there's any mistakes in this talk, to apologize to them. Next slide, please. I'd like to plunge straight in. So the picture on the top left there is Niels Bohr. He's one of the great physicists of the first half of the 20th century. He developed a quantum theory of the atom, which is sort of shown in cartoon form in the middle there. Its electrons orbit a central nucleus, rather like planets going around the sun. However, unlike the solar system, we find that only some orbits are allowed. There are many radiuses, that distances from the nucleus, that the electron cannot orbit at. There's only a few places where the orbits are allowed. So those restrictions were necessary. That restriction was necessary in Bohr's theory, quantum mechanics theory, to give agreement with some of the observed properties of atoms. Those allowed orbits are called energy levels. Quite a few years later, Isaac Rabi took Bohr's ideas and realized that under some circumstances, you could make atoms oscillate between one energy level and another. And if they did that, they'd do it at a very precise frequency, which could be used as a measure of time. And then Norman Ramsey took Rabi's ideas and was the first person to build atomic clocks. Nowadays, there's a huge network of satellites in orbiting the Earth, and they all have an atomic clock as an intrinsic part of their equipment. That allows you to have a satellite navigation device in your car. So that would enable you to navigate across the Himalayas or to find an unfamiliar address in your hometown. And GPS couldn't work without an atomic clock, which couldn't work without these quantum mechanical ideas of energy levels. Next slide, please, Holly. So here's Niels Bohr. This is another application of quantum mechanics. There's Niels Bohr with his energy levels again. These two characters, Townes and Shorlow, had the idea that if you populated those energy levels with electrons in in unusual ways, then you could induce atoms to emit light, and it would be light with very particular properties. And then Theodore Maiman here took those ideas and built the first laser. The picture on the bottom left there is a DVD or a CD, and we read the information on a CD or a DVD using a laser. So every time you watch a film or you listen to a CD, you are making use of quantum mechanics. You can use the Nobel Prize winning work of these four brilliant men and contributions from many other brilliant men to watch Shrek, or if you absolutely must, to listen to Peppa Pig. Another application of lasers, of course, is in laser eye surgery. There are some eye diseases that used to be incurable and could lead to blindness, but now lasers can be used to cure them. And the laser eye surgery is unpleasant, I understand. It's infinitely better than losing your sight. So that's another way that quantum mechanics makes itself known in essentially everyday life. Next slide, please. My equations have gone missing here. What we have here is a wave, and that's lambda is a wavelength there, and that is related to, there's an equation that should be here which relates lambda, the wavelength, to the momentum, which is the mass of a particle times its velocity. So you see what quantum mechanics gives you is wave-particle duality. Okay, it says everything is both a particle and a wave. So there's the equation here, lambda, which relates the wavelength to the Planck's constant and the momentum of a particle. So if you take a billiard ball, for example, which is about 4 centimeters in size, then you calculate if it weighs about 200 grams, and if you hit it with a cue, it moves at about 1 meter per second. You can work out its momentum, you can work out Planck's constant, and you can work out the wavelength. And the billiard ball is 4 centimeters in size, but the wavelength comes out as about 10 to the minus 30 meters. That's 1 over 1 with 30 zeros on the end, that fraction of a meter, so negligibly small. So if you have a billiard ball, you don't need to worry about the wave-like properties at all, because the wave is the wavelength is many orders of magnitude smaller than the size of the ball. When you get to an atom, let's take an oxygen atom in the atmosphere, we can measure the mass of atoms rather accurately. And in the atmosphere, they have an average velocity at room temperature, and you can work out their wavelength. An atom is about 10 to the minus 10 meters in size, and the wavelength is about 10 to the minus 10 meters in size. And when you get down to that size, excuse me, everything, when you get down to that size, the wavelength and the size of the object are the same. Then you do have to worry about the wavelength, the wave-like nature of the material of the object when you're trying to understand its properties. So that's what quantum mechanics is. Can we have the next slide, please. There's another equation missing. The uncertainty principle exists, which tells you that once something is described as a wave, you cannot sort of pinpoint it. A wave doesn't have a precise position. So there is a fundamental, one of the cornerstones of quantum mechanics is the uncertainty principle, which says that you cannot know the position of an object multiplied by the uncertainty in the position of an object multiplied by the uncertainty in the momentum of an object always has to be greater than Planck's constant over 2. Planck's constant is the constant I introduced on the previous transparency. Uncertainty is often thought of as a rather mysterious thing, but it's not all that mysterious, really. We live with uncertainty quite a lot in our everyday lives. If you have if I have a £10 note in my wallet, I can look at it and I know where it is. But if I have a £10 in my bank account, I'm very uncertain where that is. That is not located. We live with uncertainty, so it's not something to worry about greatly. The other thing is superposition. Is the next mysterious thing. We believe, if you take a dice, I'm going to take a dice as my example because Einstein is reputed to have said God does not play dice. So I'm taking a dice as the example. We believe that if we knew the initial states and conditions well enough for a dice, we could calculate what number the dice would land on, what number would be uppermost. And even if we didn't look at the dice, we believe that it would have landed with a particular number uppermost. We wouldn't know what that number is if we don't look at it, but we believe it has got a number uppermost. In quantum dice, it's completely different. The uncertainty principle means we can't know the position and momentum of the dice well enough at the same time, so at least with unlimited accuracy. So it's not possible to do the calculation of what number the dice will add up, what will come uppermost on the dice. And the dice is in a state that looks like that. It's got in the diagram of the 6 dice in the bottom right-hand corner, but it's got every number uppermost. So we think the maths tells us that we should think of the dice as having every number uppermost until we actually measure the position of what number is uppermost. So that property of having many states, many observable states at the same time is called superposition. And it's very much a quantum phenomena. But in the next transparency, I want to give you a slight feel for it. Can I have the next slide, please? Okay, so if you look at the cubes in the middle there's 5 cubes, and they're supposed to be transparent. And they're just transparent cubes. But if you look at them, then you may see them with the orientation on the left, or you may see them with the orientation on the right. Okay? And those orientations are different. So this is rather analogous to the idea of superposition. You've got the central cubes, and they don't have a particular orientation until your eye decides on one rather than the other. So it's not a good analogy with superposition, but it's about the best I can do. So the second point in this section of the talk is that in quantum mechanics, the state does not actually exist until you look at it. You have to look at it for the state to actually exist. Right, can I have the next transparency, please? The other thing quantum mechanics can do for you is change your view of reality, and I want to give a well-known example of that. Electrons, which orbit the nucleus, when you're describing atoms, as I said before, have a property. They have magnetic properties as well, and they have a quantity called the electron magnetic dipole moment. You don't need to know what that is, but it can be measured experimentally, and it's given by the number in light blue, the top number in light blue there. It's the 28 is the uncertainty in the last 2 digits. They're always experimental uncertainties, but you get that number. Luckily, you can also calculate it theoretically with great accuracy. And the value you get is the lower value there. That's under 764 there is the uncertainty in the last 3 digits, but you can see the agreement between theory and experiment is absolutely astonishing. You don't get that level of agreement anywhere else in physics. But I had to make some assumptions when you do that theoretical calculation. When you're introduced to the idea of empty space, that's what you think it is: empty space, a vacuum, nothing in it. But to get this agreement between theory and experiment, I had to assume that the vacuum was teeming with particles and antiparticles that are continually being created and annihilated. And if I make that assumption, then I get this result. This creation and annihilation of antiparticles is allowed by the uncertainty principle. It has an energy time form, so you're allowed to borrow enough energy to create particle-antiparticle pairs, as long as you do it for a short enough time that the uncertainty principle is obeyed. So you have a choice, really. When you are introduced to the concept of the vacuum, everybody thinks it's just empty space. But now you see that agreement between experiment and theory. You can accept this agreement and as significant, and then you have to adjust your view of what a vacuum is, or what empty space is. Or you can just say, well, that happens to be coincidence. It's an astonishing coincidence, but you could claim that. And then you can maintain your view of that the vacuum is just empty space. But nearly all physicists consider that very significant. Quantum mechanics is a fantastic theory of the microscopic atomic world. It gets everything it calculates properly, it gets right. Okay, so there's no need to, there's no real problems with it. However, there are a few things it has to speak on, which it hasn't spoken on properly yet. And the first is called matter-antimatter asymmetry. If you solve the quantum mechanical equations, the equations describing matter and the equations describing antimatter are completely equivalent. And so there's no reason to suppose one is preferred over the other. But in the universe, there is a huge prevalence of matter. There's virtually no antimatter, it's all matter. And so there's an asymmetry in nature that doesn't exist in the theory, an imbalance in nature that doesn't exist in the theory. And therefore, the quantum mechanics has to address that problem. Probably the most famous the most famous problem is that quantum mechanics is a fantastic theory of the microscopic world, and gravity is a general relativity. We have a fantastic theory of gravity called general relativity, but they just do not fit together. They're they just don't fit together. Most physicists think they should unify in some way, but nobody's been successful in doing that. There's a lot of people working on it. And finally, quantum mechanics has to interact smoothly with classical mechanics. As I've said earlier, quantum mechanics on the whole describes things that are microscopic, but as things get larger, the quantum mechanical predictions must become the same as the classical physics predictions, the predictions you get from Newton's laws of motion. And that works quite well a lot of the time, but there are some places in physics where we don't know how to do that, and where there's still a lot of work to do to make that borderline between classical mechanics and quantum mechanics seamless. So I'll just finish by saying, isn't this a wonderful position to be in? We have a theory that works superbly and clearly contains a lot of truth, but there are still fundamental questions to be answered, and therefore work and interesting things for future generations of physicists. Next slide, please. And thank you for your attention. That's it.
That's brilliant. Thank you very much, Paul, for taking us all the way from the basic notions of quantum mechanics to applications, and also what it all means for our perception of reality, and yeah, maybe future directions that are still left to explore. So that's wonderful. As I said before, we'll take questions at the end. So it's my pleasure, therefore, to pass the word on directly to our next speaker, who will be Claire Dunning from the Math Department, giving us a view from the mathematical side of things. Over to you, Claire.
Hello. So thank you. So not entirely from the mathematical side, I should say. So I was wondering what to call this, and I went in the end with some things quantum. We can't go for all things quantum because we couldn't possibly talk about them all, and we don't know what they all are. And also, we should follow the rule for outreach where you don't put equations on the slide, but actually this is a rather beautiful equation on a rather beautiful sculpture, and I will mention it shortly. Next slide, please, Holly. So there's a question here, and Paul has already produced, shown one of the pictures here. He's shown the atom in the middle there. And the question is everything actually made from something? So when we were children, we might have asked, you know, what are we made of? What is that piece of wood made of? Or in this case, the matter label here looks like water. So what's water made of? And we know that it consists of the molecules H2O, so 2 hydrogens and 1 oxygen, but each of those atoms itself is made up of constituent parts, and the constituent parts are something in the center. Well, as you would have learnt at school, there's something in the center that's called the nucleus, around which, and this is the school picture again, there's some electrons. How many depends on which particular atom we're looking at. But then if we sort of peel back the insides of the nucleus, and that's not a scientific term, that's not what we actually do, we find it's made itself of smaller bits. It's made of protons and neutrons. And the sizes we're at here, so Paul said the atom is about 10 to the minus 10. The nucleus is about 10 to the minus 15. So these are really, really small objects. And the protons and neutrons, we don't stop there. So when you look closely at these, normally by putting them in a really big experiment, like the LHC at CERN in Geneva, you find that they are themselves made up of constituents. So they're made up of, in the protons case, by 2 types of quarks, the up and down quark, 2 of the up and 1 of the down, and the neutron, it's the other way, 1 of the up and 2 of the down. So these fundamental particles, the quarks, these are really tiny. We don't know how small. They're definitely less than 10 to the minus 16, but we don't have a size for them. And the question would be well, is everything made up of something? Are the quarks, if we manage to peel them back, are they made of something else? Or are in fact, they don't exist at all? Okay, so sorry, next slide, please, Holly. Okay, so moving on to this slide. So this is a rather beautiful sculpture. It's 8 meters long, 3 meters high. It's by Tremois from 1977. It's in bronze. You can find it in Paris in the Châtelet-Les Halles train station or metro station. So next time we're allowed to travel, go there and look at it. So over on the left, it's got some beautiful images of the structure inside an arm, but over in the center and to the right, it's actually got some really important equations from the perspective of quantum mechanics. So one of them at the bottom is actually the Heisenberg's uncertainty principle for position and momentum that Paul mentioned. That tells us that the more we know about the position, the less we know about the momentum. So we don't know where anything is in quantum mechanics. We've got the energy of the photon, so the particle of light, that's the one on the left on the sun. And then one of the arms of whatever this thing in the middle is, has got Schrodinger's equation. So it's one of the key mathematical equations in quantum mechanics. It's also on Schrodinger's bust in a slightly different form there. And from a mathematical perspective, this is a straightforward thing to solve. So undergraduates learn how to solve such equations. Of course, undergraduates learn how to solve ones you can solve, but that's not the reality. The reality is you'd have to do something. You wouldn't have one that you could solve exactly. But roughly speaking, you plug in this V you can just about see in the middle. It's the potential. It would describe where your particle was sitting, and then you probably add in some conditions as to what happens at the edges of the world in which your particle lives, and you can solve it. And what comes out of the mathematics is some really interesting consequences. So next slide, please. So, particles with a really big P. So some of the consequences Paul has already mentioned, one of which is we don't know where anything is anymore. So we can only know the probability of where your particle might be. So the image on the bottom right here, this is the related to the hydrogen, and we're looking at the probability of finding the electron orbiting the nucleus here. So, and the different colors, you can see that there is a red, there's a sort of a yellowy orange, and there is some white. So, and if for anybody who hasn't used Zoom, there's a little grey bar between me and the slides. If you slide it left to right, you can make the slides bigger and me smaller if you want to see the images a bit more. Okay, so what do these pictures tell us? Well, it's the white is it's really probable that the electron may be found in the white areas. It's medium probability they'll be found in the red areas. And then the black areas, the probability is actually 0. So this says, we can see there's quite a lot of black in each one of those images. It says that the, so sorry, Carlos is just commenting on the joke in the football image there. Yeah, it's saying that the particle can't actually be in these areas. So questions like, is the particle here or there, are no longer a trivial thing. Particles and waves, Paul has already mentioned. So the image at the top right is the first picture of that, very recent times. And then another important consequence in quantum mechanics, and it comes out of solving that equation due to Schrödinger in a very simple case, is that energy comes in lumps. So it comes in quanta. Yeah. So, but it's not just energy, it's many other quantities such as momentum and some angular momentum, and then spin, which is something that isn't what you might think it is. So this is really strange. So I saw a very nice analogy somewhere on the web that said it's a little bit like getting in your car and you can drive at 40 miles an hour and you can drive at 50 miles an hour, but there is no 45 and there's no 42. So the speed of your car is normally continuous, but in quantum mechanics, things come in lumps. Okay, so on to the next picture. Slide, please, Holly. So, now, quantum mechanics is fabulous, but it really works really well for a small number or a single atom, and they shouldn't be going very fast. Or if you have really fast electrons, so relativistic electrons, then you need to make some adjustments to the standard equations you might use, such as Schrödinger's equation. British theoretical physicist Dirac, he wrote down the relevant equation, and it's actually on this slab, which is in Westminster Abbey. So you can see in the middle here, it also has his equation in the center of that slab, so you can go and stand on it if you want. And Paul has alluded to this already. When you solve this equation, this is for the electron, it gives you 2 solutions. So one of which is related to the electron with a negative charge. So conventionally the electron has charge of -1. And then there's a second solution, which is for an identical particle. It has the same mass, it has the same spin, but it has the opposite charge. It has charge +1. So Dirac actually predicted antimatter. He said there should be, to every particle there is an antiparticle, and for the electron there is the positron. And it was discovered experimentally, and they exist out there. They're just not as many of them, as Paul said, as there are particles as opposed to antiparticles. Okay, so next slide, please, Holly. Okay, now I said that when we start looking inside the atom, what we discovered was the nucleus, and we discovered protons and neutrons, and then we discovered quarks, and we're not sure if they are the fundamental object or the sort of the Lego bricks of our world. And in fact, some would say they don't exist at all. So the things that do exist are something called fields. So before I get to quantum fields, I wanted to give you a sense of what we mean as mathematicians, physicists, mathematical physics or theoretical physicists by fields. So I don't mean the green things with currently covered in snow. I mean fields that you are familiar with, although you may not be aware that they are a field as such. So the first is the gravitational field. It's what's keeping you sitting on your chairs, me sitting on my chair. When I jump up from my chair, it brings me back down to my chair. So that's the image on the bottom left-hand side. So that's probably the Earth and the Moon. Another field is one related to magnets. So I have, in fact, I can't, there we go. Now I can see myself as well. So I have some magnets here. I don't have a bar magnet at home, but I do have some magnets from the pin board. And you know, with your magnets from the pin board, oops, so they will either repel, or these ones, if I line them up correctly, they will attract each other and join together. Now, if you have a bar magnet, which is shown at the top left here, then it's got north at the one end and south at the other end. So north here is at the left. If you put it on a piece of paper with some iron filings, so tiny, tiny bits of iron, the iron filings all line up, and this is a photograph. So this is a bar magnet, and these iron filings are all lining up, and they're lining up along lines on that piece of paper. So the image on the right-hand side are these, the lines of the magnetic field, analogous to the gravitational, the lines. Similarly for electricity, we've got here the other picture on the right hand side, the far right here. We've got a positive and negative charge, and we've got some field lines, we call them, in between the two. So the point about fields, it's a little bit like waves, in the sense of a wave exists everywhere, and these fields, also exist everywhere. So can we have the next slide, please, Holly? Okay. And what we would perhaps think of is in modern quantum mechanics is we want to describe those building blocks of everything, of life, etc. And what we should be thinking of here is we haven't got particles anymore, we've actually got fields. So fields, as I said, it's going to be something that has a value everywhere in space. Sometimes it has a direction as well, in the sense of when you're in your car, you know what speed you're doing, but you also know whether you're going forward, backwards, or wherever you like. And all of the standard elements of the standard model, which describes the best possible description we have so far of the world, I've put some here. We've got some particles. So on the left, we've got the quarks, we've got the up and the down, we've got the electron, and we've got some forces. And in the middle, we've got a picture of the Higgs boson. Well, the understanding we would have from a perspective of quantum field theory, which is when we marry classical field theory with special relativity and quantum mechanics, is everything is a field. And so everything is like a wave extended everywhere, and the particles are sort of localized excitations in those fields. So with the electron, there is something called an electron field. With the up quark has its own field. The Higgs boson has its own field, the Higgs field. And when the fields, you have these excitations, they can transfer energy from one field to the another, and that might be in your accelerator. You have a particle colliding with another particle. So the perspective we might have here is when Graham said, what are things, is we might say, well, actually, there are no particles from the perspective of this quantum field theory, which again has can be tested fantastically accurately, is everything consists of various different fields. Okay, and if we go on to the next slide, please, Holly. Okay, I wanted to give you a sense of something that is really very recent, and also because we have lots and lots of fabulous men, but there are some fabulous women who've made amazing contributions in quantum science as well. So I want to talk about really cold particles called fermions. Fermions have spin a half. So the image on the left is a snowman that some friends' children made yesterday. The image on the right is at the bottom is Deborah Jin, whose team created this fermionic condensate. So there are not just 3 states of matter. So the snowman on the left, that's water in ice form. It will eventually melt into water, which is in liquid form. A little bit of it might evaporate if it gets particularly warm, which would be in gaseous form. But we have much more complicated quantum states of matter now, so including plasmas, Bose-Einstein condensates, which were predicted by Bose and Einstein back in 1924-25 or so, first discovered in 1995, and the people got the Nobel Prize for that. And then a much harder problem is to produce a condensate with these things called fermions, and Debbie Jin's team did that in 2003. So there was talk that they might get the Nobel Prize for this in the sort of the last decade or so, but sadly Debbie Jin died of cancer. So, but there's all sorts of intriguing exotic quantum phenomena that quantum mechanics has a really key role to play in condensed matter physics as well. So it's a really, really broad, exciting field, and some of the people on the panel know far more about all of that part than I do. So, but thank you. Pass you back to the chairs.
So thank you very much, Claire, for that fascinating tour through many of these aspects of quantum theory, from quantum mechanics to quantum field theory to really cold stuff, many aspects, and we'll be coming back to a lot of these in the discussion later. So particularly if you have any questions or things you are interested about it, please start putting them in the chat, and we'll try and wind these into the discussion when we get there. But for now, let's move swiftly on to our next perspective on quantum theory, which comes from computing, or at least somebody who works in a computing department, if I want to be precise. Welcome, Carlos.
Thank you, Sam. Thank you for the warm introduction, and thank you for having me here. So I'm going to go very quickly, because I do think that everybody is waiting for the main dish, which is the discussion afterwards. So I just want to talk about applications of quantum technologies, and I'm going to be calling them quantum information technologies. Next slide, please, Holly. So what does it mean when I say quantum technologies? Well, yeah, next slide. That's fine. Let's show the chair. From a very basic perspective, everything is quantum mechanical. Quantum mechanics is simply our best theory of the world. So everything is quantum mechanical. So every technology is a quantum mechanical technology. We don't fall through a chair, even though most of the chair is empty space, because of quantum effects. But that's not what I mean when I say quantum technologies. So next slide, please. So technologies, when we think of quantum technologies, these are technologies that actually make use of these quantum effects that are understood thanks to quantum mechanics. Next, please. So here's some examples of quantum technologies that my colleagues have already alluded to. Microwaves, lasers, fMRIs. But once again, these are not the technologies that I want to talk about here. Next slide, please. Next one. Rather, what I want to talk about is technologies that use the quantum effects that mystify us, the quantum effects that we don't see every day, the ones that we have to work very hard to obtain. So some examples, which I'll delve into more deeply in a moment, are what you see on your screen: quantum computers, quantum metrology, quantum communication. Next slide, please. So what are these quantum effects? I'm not going to go into a deep explanation of these, first, because as I said, I'm mindful of the time, but also because my colleagues that have spoken before me, Claire and Paul, have already done a very good job of explaining these to the extent that one can explain in a venue such as this one. So I'll just very briefly mention them. We're talking about quantum coherence. 5-second explanation is the state of the quantum state is kept completely rather than losing parts of that state. That's very a very poor, but only kind of explanation I can give in 5 seconds. Quantum interference, you've already heard about the duality that matter is both a wave and a particle. And because they're waves can interfere with each other. You already know about this because lots of you have, if you don't have them at home, you at least know about noise canceling headphones, which detect the waves coming in and emit waves that are in the opposite phase, so they cancel out. We can use that quantum mechanically to make things cancel out with themselves. Superposition or quantum parallelism, again, this has been explained before. Basically, if you haven't measured something, that something can be best described as, very briefly, as being in more than one state or in neither, which can be very confusing, but can be very useful when trying to create new technologies. Then there's quantum entanglement, which again, I won't go very deep into, and wave function collapse, which is what happens when you measure something. Before you measure it, it can be in more than one state, but once you measure it, you force the state to evolve into one definite possibility, into one definite state within that realm of possibilities. Next slide, please. So the first example oh, give me just 1 second. So quantum computation is our first example of a technology. And what it does is it makes use of coherent superposition entanglement to accelerate computation. The main, I guess, the punchline here is that quantum computers can accelerate lots of different computations, many, slightly. Not very, but because it's very applicable to many types of problems, this is important. But there's very few problems, not a lot, but there's very few problems upon which quantum computers can give a drastic improvement, what we call an exponential improvement. Next slide, please. So I've put down several examples in these two columns. So a polynomial advantage, that's a slight advantage, that's a lesser advantage. Some things that we know can be applied, fall into that category, is decision problems, which if you're a computer scientist, you know exactly what I'm talking about. If not, the quick explanation is that pretty much any problem, any mathematical problem, can be stated as a decision problem. And so quantum computers give a way to accelerate all decision problems over what we would call the naive algorithm. So if you don't have a better algorithm, rather than searching the realm of possibilities for your answer, then a quantum computer can do that faster. And there's lots of problems for which we don't have a better algorithm than that. There's some graph problems and machine learning, which is very much in vogue nowadays. You can imagine that thanks to quantum computers in the near future, Amazon will start giving you better recommendations. So what are some things where we get exponential advantage? Well, protein folding is one, simulation of quantum systems being the broader set that encompasses that. We also have subgroup finding problems, and that might not say a lot to you, but one particular subgroup finding problem is factoring, which is if we take two numbers together, say 7 and 5, it's very easy to multiply those together. Multiplication is easy. But factoring, if I give you 35 and I tell you what two numbers, other than 1 and 35, of course, give me 35, that's a much harder problem. And it's much harder for classical computers. It turns out it's very easy for quantum computers. Next slide, please. I'm going to give a very quick interlude because I think this is important. There's this thing called public key cryptography, which again, if you're a computer scientist, you know exactly what I'm talking about. If not, you can think of it as a technology that's behind all of internet security. So internet banking, when you connect to social media and you can connect to your social media account, but nobody else can. Things like cloud computing, secure web browsing, science software, pretty much all of the internet uses public key crypto in one way or another. Next slide, please. Now, all of current public key cryptography relies on what we know as one-way functions. These are functions that are easy to compute, but difficult to the reverse. The example of 7 times 5 is easy. What are the factors of 35 is hard. Next slide, please. Now the problem is that factoring is easy for a computer. Next, please. How easy? Well, let me give you an example. RSA 2048 is currently the gold standard for public key crypto. The reason it's the gold standard is because if you use a classical computer to try to break RSA 2048, and that classical computer is extremely fast, so it's a 10 gigahertz computer, and I say, can you please just brute force this RSA 2048 crypto system encryption, it would take you roughly 1.2 million times the age of the universe to calculate that. If instead of giving you a classical computer, I gave you a quantum computer that is not the most powerful, but not the weakest, you'd be able to do that in 14 minutes. So that's drastically important. And it's one of the reasons why there's so much interest in quantum computing from the cybersecurity side. Next slide, please. So another application of quantum technologies is what we call quantum cryptography and cybersecurity. So here what we're using is superpositions, wave function collapse, in order to protect or secure our data. The punchline here is that because every observation is a physical interaction and measuring something or observing something will cause its state to collapse, eavesdroppers, intruders on our data can be detected. Next slide, please. Here's an example. So suppose Alice wants to send Bob a secret message. Now, if Alice encodes that message in a series of bits, zeros and ones, he can transmit that information over a wire to Bob. But then a problem emerges. Next slide, please. An eavesdropper, Eve, can read that message in transit. And we don't want the eavesdropper, Eve, to read that message. So what can Alice and Bob do? Next slide, please. If instead of encoding the message as a series of zeros and ones and transmitting them as classical information, we transmit it as quantum information, and say we use the states of photons, the polarization of photons, or the spin of nuclei, or the spin of electrons, or any other particle, and we transmit the information like that, then Eve might still be able to measure it. Next slide, please. But because of the uncertainty principle that Paul already alluded to, she won't be able to obtain the message intact. More importantly, though, next slide, please. If she tries to measure it, Bob will realize that there's an intruder because her act of measuring changes the state that Alice sent to Bob, and this can be detected. So nature comes with its own tripwire, its own intrusion detection system. That's really cool. Next slide, please. So applications of quantum crypto, quantum cybersecurity can be applied in plenty of areas. I've already mentioned secure communication, but we can also do secure cloud computation. And with colleagues here, we're working on more secure or guaranteed random number generators. Next slide, please. Another application of quantum technologies is metrology, imaging, and sensing. And here the idea is to use coherence to obtain a better result, a better measurement result. And the main insight here is what we're trying to do is, instead of repeating an experiment lots of times and getting some probabilistic outcome and then using statistics, what we're going to do is we're going to bunch all those experiments into a single large quantum experiment, so that instead of adding probabilities, we're adding amplitudes together, and that allows us to get a quadratic advantage over any classical procedure. Next slide, please. So this has a myriad of applications in imaging, astronomy. There's quantum radar, lithography, which is sort of the opposite of imaging. It's creating images. Next slide, please. Finally, I'd be remiss if I didn't mention one of my favorite applications of quantum information, which is looking back at physics and trying to understand it better. John Wheeler, a famous physicist and philosopher, or physicist that did philosophy, famously said, "It from bit, and hence the quantum." Claire and Paul have already talked about quanta of matter. So light has quanta, they're called photons. It turns out that information has quanta. The quanta of information is the qubit, or the bit. It's from bit, and hence the quantum. And the fact that information has quanta is so profound. It allows us to see the world in a completely new way. one of the deep modern insights, more modern, is, for example, Lee Smolin, where he says that what we know of the world, or our inference of the world, is as much epistemology as it is ontology. When we ascribe a state to a system, that state doesn't belong to the system. It belongs to the relationship between the system and us. And again, there's so much more to say than what I can say in a minute. So I'll just leave it here, and hopefully we can come back to this in the discussion. Next slide, Holly. One more and we're done. Thank you very much.
Excellent. That's brilliant, Carlos. Thanks very much for explaining what it means to have a quantum technology and what we might be able to do with it, and really how we could use them even maybe to understand the world around us. So that actually is a fantastic transition to our next speaker. So thanks for lining up your talk so beautifully. So it's my pleasure to hand over the word to Graham Forbes to give us his view from the point of view of the philosophers.
Excellent. So yeah, thanks very much for having me. It's always sort of odd to be invited to a panel like this, because there's a lot of what my colleagues are doing that I just really can't compete with. Like if we need to find out how to think about maths, Claire is the person we should go to. If we need to do stuff with this, we've just seen all the technologies that get involved. I can't build you an MRI machine for toffee, you know, like, my job is mainly to get really confused by things in a way that hopefully other people find productive. So we've got a nice image that looks like a visualization of physics there. No idea what that's supposed to represent. It just looks like garbage. It's just someone's made some pretty shapes on a thing. Next slide, please. So there's a bunch of things that get claimed for quantum theory. And they always kind of alarm me because we get some quite radical claims. So we've got some stuff to come up if you do some clicking on. So the entire universe is conscious. That's not what quantum theory shows. That chairs, cats, and tables aren't real. Quantum theory is not in a position to show that. That's a much trickier question. That there's a difference between non-conscious rocks and non-conscious and conscious people. Sure, I treat rocks differently to the way I treat people. Quantum theory by itself isn't going to tell me what that difference is. We're probably going to need some psychology at some point. Anything to do with free will. As far as I can tell, free will is to do with whether there's the right kind of connection between what you want to do and what you're in fact able to do. And whether you have a deterministic or indeterministic interpretation of quantum mechanics probably isn't going to make much difference to that distinction. I mean, that one's somewhat more controversial, but you get a lot of claims that I think involve having something that's exciting and mysterious and then trying to like throw it at some difficult philosophical problems. And actually we got to respect how difficult the philosophical problems are, that they're not going to be that easy to solve. Next slide, please. Okay, so one of the things that philosophers spend a lot of time doing when they're not just panicking about, you know, claims that we've discovered quantum consciousness, whatever that is try and work out how we interpret what's going on when we are doing things. So we've got a lot of maths. We've seen some of the equations. We've got various different ways of interpreting those equations. One of the things philosophers of physics tend to do is really think very, very carefully about how we should understand what the math says as a description of the world. Because there's always a step from going, look, this spits out kind of things that we can use to actually working out how they represent the world to be, what the numbers or variables or whatever stand for. So here's a bunch of people, Karen Crowther in Oslo, Tim Maudlin at NYU, Alyssa Ney in UC Davis, Oliver Pooley in Oxford, Christian Wuttrich in Geneva. These are the people that I phone up when I need my quantum fixed, you know, like what's going on. They've all got like at least a degree in physics and lots of experience in philosophy. They really know their stuff. I'm not one of them, right? I'm just a philosopher of time who kind of gets my sums double checked every time I go anywhere near a quantum. Next slide, please. But here are some things that it's useful to think about. So the kind of demands that a philosopher of physics makes on a physicist is expressed quite nicely by Tim Maudlin here. A physical theory should clearly and forthrightly address two fundamental questions. What there is, that's ontology, which we've heard a bit about earlier, what there is and what it does. Now, we've heard a lot about what it does. What there is the bit where quantum theory gets really strange, that we're really good at doing stuff with it, but we're not sure what it says there is. Click on. Okay, so one of the things we're interested in philosophy is what categories we're talking about. So when we're describing the world, what kinds of entity, what items does that world consist in? So ones that we're fairly used to involve things, things like this pen, you can count, stuff like the water in this bottle. You say you can measure how much of it there is, but you can't count it. Events last a certain amount of time. Processes not only last amount of time, but they change over that time. States of affairs, they're individuals having a property. So I'm sitting, that's a state of affairs. And then we heard a bit from Claire Dunning about fields. So fields, unlike things, where things stand in relation to other things, fields just have lots of internal relations. So they're spread out, and then they vary within their within themselves. So one of the big questions we're worried about in philosophy is, what categories is our best theory of matter actually telling us the world is built on? And we had this sort of idea we saw that we're maybe building up from gluons and quarks up to that idea of building up small things into big things. As we saw, like that might just not make sense. If we don't think things are the right category, claims about how we build from small things to big things just aren't going to be helpful. Next slide, please. So we saw in Paul Strange's talk earlier the claim that everything is both a particle and a wave, and then we later saw that everything is a field. We're not even sure when we say everything, which kind of things everything's supposed to cover here. Click on. So maybe one of the problems that leads to talking about wave-particle duality is that we think that waves and particles are our two options. So both of these are venerable categories in the history of science. Particles come from the corpuscularian view of matter, which we get from the 17th century. So this is very crudely the view that everything is made up of tiny, tiny billiard balls bashing into each other. So it was really foundational in thinking about mechanics. And then we get wave theory from the 18th century, where we start having good mathematical descriptions of those, really useful for electromagnetic radiation, among other things. But both of these are kind of based on metaphors that we can get a really good grip at, really good visualization of with macroscopic phenomena. So we've got a billiard ball, we can play billiards with each other and call it research. That's fantastic. We can get slinkies and we can do longitudinal or transverse waves. If you're like me, you probably did those at school. The reason that we end up having to say strange things with wave-particle duality might be that we're treating the world as if it's made up of tiny, tiny billiard balls and tiny, tiny slinkies. And we're trying to work out how they can fit in the same description of the world. So maybe the move to fields is the one we want to go, or maybe something else again. Maybe we just haven't got a good label for the category yet. The quantum state or phenomena or wave function, maybe we just need a new category altogether. Next slide, please. Okay, so then we get on to superposition. So this is the one that really worries people a lot. And people think it's got these really sort of profound philosophical implications. So philosophers spend a lot of time being confused by it. So how can something be in two states at the same time? Click on. So the question kind of presupposes that we're talking about a system being in two incompatible states. But of course, if they're incompatible, they surely can't be in both, because we just said that that's what incompatible means. So why not some third state, which is neither both, nor one by itself, nor the other? And actually, if we look at the little table there, you know, there are 4 options. The logic for neither is just so much easier than the logic for contradictions for both. So one of the things that philosophers tend to do is try and think through the implications of some of the claims that get made, to see if we can make sense of them, and see if we can come up with kind of helpful metaphors that that enable us to make sense of this stuff, rather than just getting on with it. Next slide, please. So finally, the other mysterious thing that was said earlier that that is worth thinking about, claims that the state does not exist until you look at it. Click on. So we've got this question about what we mean by look. So really important to be clear here. Vision has nothing to do with it. We could set up an experiment that makes a clicking sound, so we know what's going on. We don't need it to be visual, and it's got nothing to do with conscious observers. This is where people think there's a connection with consciousness. There really doesn't need to be. We could get a machine that like prints all this stuff out straight into a bin, and then archaeologists come along like 200 years later and dig it up. The collapse doesn't happen when the archaeologists dig up the printout. The collapse happens when the measurement happens. So what we're talking about here is a specific sort of causal interaction in which one attempts to extract information from the system, and the interaction changes the system, and so changes the information. We had a nice illustration of eavesdropping earlier as an example of that. So looking at it is an attempt to mess with it in a way where you get information out, but getting that information out changes what you're looking at, precisely because you give it a good poke, and that's messed it up. So we then have this really difficult to answer question: what does it look like when it's not being looked at? What does it look like when it's not being measured? Really hard to tell. Some physicists and philosophers are going to want to say there's just no answer. We can't even make sense of that question. Others are going to want to say there is an answer. It's just really hard to find out what it is. And so this is where we think of it as a difference between epistemology, what we can know, and ontology, what there is. Next slide, please. Okay, so there are a bunch of interpretations I just want to wave my hands at. Don't bring them all on just yet, because it'll go too fast for people. So we've got the GRW interpretation, which is one that really thinks it's the collapse. It's when you measure, that's the thing that we really take seriously. And then we're kind of not sure what's going on when you're not measuring anything, and we shh. But we really think what there is the things you get when you measure. That creates some difficulties. Click on. Okay, then the Broglie-Bohm interpretation. Now this one is the one that kind of makes the most sense. It's not clear it's true, but it makes the most sense. So this is the one where you think maybe everything really is made up of tiny, tiny billiard balls and tiny, tiny slinkies. And we just got this theory about how they work together to create the kind of phenomena that we see. So that at least we've got a good idea of what the categories we're dealing with are. We just need to check whether we can actually make sense of the phenomena that we get out at the end. Next one, please. So the Everett interpretation is the one that probably comes up most in philosophical conversations, because it's the one in which reality branches, often described as many worlds, though philosophers don't like that because world is a technical meaning for us. But basically, everything happens somewhere, and we've just got this problem of not knowing which bit we're going to be in. But this is a deterministic view in that everything happens. And we know exactly what's going to happen. It's going to be everything. We just don't know which bits we're going to observe. Next one. Right, now we've got the Copenhagen interpretation. So it's worth mentioning that this one isn't really a theory. Like, the others actually tell us what Maudlin wanted, what there is and what it does. The Copenhagen interpretation gives us a nice recipe for getting results out, but it doesn't really tell us what there is. I mean, there are some ways of thinking about it where it tells us that what there is somehow radically indeterminate, that there's something going on and we don't know what it is, as Bob Dylan famously put it. Mainly it's described as the shut up and calculate view, where people who think that these philosophical questions are best left to the philosophers and just want the maths to work, get on with the Copenhagen interpretation and leave the problems for later. And then click on, please. And then we've got the, hey, but we know quantum theory by itself can't explain loads of things. We need to get it to play nicely with the general theory of relativity. So we have quantum gravity, or we want to add field theory in. So we get quantum field theory, and then just things get incredibly complicated. So we need to work out what fields are. We need to work out what causal sets are. We need to work out whatever those theories talk about. And there's a lot to say about that we're not remotely going to have time for. But hopefully that's given you kind of a sense of where the philosophical action is a lot of the claims that people make, particularly in these contexts, trying to explain what's going on in quantum theory, rely on sort of metaphors to get your head around things. Actually working out which metaphors are useful is a job by itself. And that's one of the things that philosophers of physics do. Cool, next slide, please.
So I guess you've stopped.
Oh yeah, sorry, I have stopped. Yes, that was the stopping was the.
Yes, fantastic. So thank you, Graham, for that overlook. As physicists, we sometimes said we never understand quantum mechanics, we just get used to it. But actually, I think you've convinced us that to make progress, we do actually have to understand some of it. And maybe us all speaking to each other more often, like in this event, would actually be useful, not just for informing our students, but also for actually making progress in research and so on and so forth.
I can recommend a couple of books if people want to think about the philosophical issues.
Yeah, not just yet. You can put that in the chat maybe. So with this in mind, we've now finished the starter of this event, which basically was these 4 introductions to 4 different aspects of quantum mechanics, or more from 4 different viewpoints. And so I think we've discovered that quantum mechanics wasn't invented just to torture undergraduates. We've heard about from the fundamental to the useful. We've heard about from the abstract to the downright bizarre. And I think now is a good time to bring the entire panel together to discuss some of these things, okay? And the way this discussion will work, we decided, is we have 5 discussion points we're going to try to get through, each one which is going to be a catalyst to discuss some of the questions raised by these talks and some other things. And for the first one, we start 100 years ago in 1921. Okay, so it's 2021 this year. 100 years ago was 1921. If you cast your minds back to this year, in London, a magician sawed someone in half for the very first time. In Canada, some really smart biologists had isolated insulin for the first time. In Ireland, a group of people was inventing Ireland. And in Germany, 2 physicists were plotting one of the first direct measurements of quantum mechanics in the early days of the theory. And to tell us about this is a perfect opportunity to allow our bonus guest, Nigel, who isn't just an astrophysicist, formerly a molecular physicist, head of department extraordinaire, etc. But he's also a bit of a history buff. So he's going to introduce this topic, and we then open it to the panel for discussion.
Thank you very much, Sam. Yes, 100 years ago, quantum mechanics was being born. We'd had literally the born atom a few years before, and the first experiments were being done. And people were kind of coming up with conceptual experiments, and they wanted to say, well, okay, you know, let's try and explore what atoms can do. Now, Otto Stern was the person who came up with the idea of the experiment, and he wanted to see what sort of effects you would have if you passed atoms through a magnetic field. In the particular case, he looked at it silver, to see whether there was this idea that there may be some quantization effects in atoms of some fundamental things. And the particular one he was thinking about was momentum and angular momentum. The experiment was performed in 1922 by Gerlach, and demonstrated, as you can see in this experiment, that indeed there is such a thing called spin and angular momentum. It's very important now. Most, like MRI scanners, are based on this principle. But as a kind of amateur historian, I also like to think about people. And the interesting thing is to look about these, you know, these people who do these experiments and come up with these ideas. They live same lives like us. Otto Stern was Jewish, and so he had to leave Germany in the 1930s and went to America. He also holds the record for, I think, being the most number of times of any individual being nominated for a Nobel Prize, 84 times. And he got the Nobel Prize in 1944, and he's one of the few people who got the Nobel Prize for physics on his own. Gerlach, on the other hand, stayed in Germany and did his experiments, and is famous for lots of other experiments as well. Went all the way through the war, and was actually, at the end of the war, he was captured by the British and brought to Britain, and he was one of those scientists who was being interrogated and left to sort of see what he'd been doing with the German bomb. And so that, I think it's always interesting to read lives of people as well and find out what they were doing. So it's a classic experiment. And the question I would always ask, and perhaps on this one for the panel as well, is how much should we learn not only about the science, but also about the history of science?
Okay, fantastic. Thanks, Nigel. So anybody else want to comment on this? What is quantization? Does it mean something? What was known about it in 1921? Because of course, the Schrödinger equation, which Claire talked about a lot, was of 5 years after this. So yes, go ahead, Graham.
Hi, just to throw in some kind of ancient Greek philosophy while we're here. One of the major disputes that was in ancient Greece was whether we thought the world was made up of continuous things or things that were as small as it went. So you have atomism in an older sense of the word atom, as the view that there are smallest bits of the universe. And so the idea of quantization seems to inherit this thought that there's kind of smallest packets of things. And so actually, like the idea starts off with people like Democritus, and kind of gets picked. So it was always sort of one of the options in the water, that there's a smallest amount of stuff. And then we start working out, like, is this true? Can we experimentally show it? So that pedigree is quite interesting, I think.
If I may, bringing it back to the Stern-Gerlach experiment, this experiment has an important place close to my heart, because I learned quantum mechanics for the first time based on the Sakurai textbook, which starts pretty much with introducing the Stern-Gerlach experiment. And it's not here on the slide, but I find the most interesting thing that we get out of a Stern-Gerlach type of experiment is the sequential one. So you measure angular momentum in the Z component, and you get your bimodal distribution. right? And now you get rid of all the ones that have Z minus component, and you just let the ones that with Z plus. Now you measure the X component, right? Now you hadn't measured the X component. What you'd expect to see is 50-50, and indeed you get 50-50. But then suppose that you measure the Z component again, right? So let me repeat what's happened so far. You measured the Z component, and you only kept the atoms that had Z plus. Now you measured the X component, you let them all go through, but you got 50-50. Then you measure the Z component again. Our intuition tells us that because we only had the atoms that had Z plus momentum, when you measure the Z component again, you get only atoms with Z plus, but that doesn't happen. What happens is you get again 50-50, which should blow your mind. And I want to point at this one because it's the small point of contention or disagreement with Professor Strange's talk, which was excellent in all ways. But when he said that we shouldn't be mystified about uncertainty, that's I think where we part ways a little bit, because we should be mystified by the uncertainty as displayed in the Stern-Gerlach, right? Because it's not just lack of knowledge. All of us have very good understanding, and we have a lot of experience with uncertainty that comes from lack of knowledge. If I roll a dice, then I have to attribute some probability distribution to the roll of the dice up until I look at the dice, but that's only because I don't know its state. Right? Quantum mechanics is different. Quantum mechanics tells us that we can know a state of the system precisely and still not know the outcome of a measurement. And Stern-Gerlach experiments was one of the first places where we saw that, and I think that's extremely profound. That's all I had to say there.
Brilliant, Carlos. Do you want to respond to that, Paul, or shall we leave it there?
I will do. I mean, I actually agree with Carlos. My statement was that we live with uncertainty, as I stated in my bank account analogy. Not that it's not interesting and important, and certainly the sequential Stern-Gerlach experiments are an extremely good illustration of that. I'd like to respond to both the points made by Nigel. Should we understand the history of physics? Well, I think it's absolutely key. Although physics is a mixture of maths and experiments, the things that scientists in the past had to go through and what they did, and the lives around their science, can often be a source of great inspiration and a source of great, awe at how they managed to do their science. Tycho Brahe, the famous astronomer, he measured the positions of planets and moons for something like 20 years. Something, sounds incredibly dull, but he had an incredible life outside that. I mean, he lost his nose in a duel over a woman. He did astonishing things beyond just physics. So putting the physics life of someone in that context, I think is very valuable and can give a lot of context and understanding and inspiration. On the initial Stern-Gerlach experiment, what the Stern-Gerlach experiment shows you is that atoms possess an angular momentum that wasn't really an intrinsic angular momentum, which wasn't known previous to the experiment, and it's called spin. And we know the maths that describes that very well, but you should not think of it beyond the simplest models as a classical spin. We also know that, and we don't know anything much more about it. I've had a couple of fourth-year projects over the years where I had students set up simulations to try and investigate what spin was, and in the end we couldn't come up with anything much beyond spin is something that obeys the mathematics of rotational motion. The only thing beyond that we came up with was that we think there is an uncertainty principle between angular momentum and angular position. And that's important in understanding spin. But that's the only addition we could really make to the maths. Okay, thank you.
Excellent. So I think this is a great point to draw this discussion to a close and move on to the next topic. So as we can see,
could I just add one final thing? I don't know if there are any chemists.
Well, you can,
if there are any chemists present, but the other thing about the angular momentum experiment of Stern-Gerlach was one of the things that came out from it, of course, was the Pauli exclusion principle. And that's very important. And I think it's also important to remember that although we talk ourselves as about physicists and chemists and everything else, there is a uniformity in science. And this experiment might be seen as a physics experiment, but the consequences for, say, something like chemistry and all the chemistry we know was immense.
Thanks for adding that on. My comment in closing was that it doesn't take anything very complicated to really mystify us and actually show us how many deep insights we can derive from that, repercussions into all sorts of different disciplines. However, here we've just been talking about one single, quantum mechanical degree of freedom of an atom at a time. And as Sam will now explain to us, actually things get a whole lot more complicated if you look at more than one particle at a time. So over to you, Sam, for the next topic. And if you could have the slide for that, please, Holly.
Yes, so quantum mechanics, as many people read about it in textbooks and you learn about it to begin with, is about what happens with one electron or one quantum particle. But very rarely do we look at just one electron. And one of the most bizarre aspects of quantum mechanics, as if everything we've said so far makes perfect sense, is what happens when you have two of them. And the point is that two electrons are really absolutely the same, okay? Not just similar, really the same. Usually when you swap two objects, even if the objects look the same, you know you've swapped something, you know you've changed something because you've swapped them around. But actually in quantum mechanics, these are so the same, so similar, that when you swap two particles, it's equivalent to not doing anything at all. And that's something called the identity of particles. And actually, many of the effects of quantum mechanics come down to this rather than the weird superposition and everywhere at once features of single particle quantum mechanics themselves. And the theory, what happens when you start putting a lot of them together is you build up from the microscopic, which we can't see, to the macroscopic. And I've put a few quotes here, which you could read if you want on the screen, but perhaps the most apt is that more is different, okay? There's this thing called emergence. You put a lot of things together, and what you get out is more than the sum of its parts. So that introduces this. This basically is taking us from quantum mechanics to the topic known as quantum field theory. And perhaps Claire would like to say something more about this, given that she introduced quantum theory, field theory in the first place.
So possibly I said quite a lot about it before, although not particularly in any detail. I saw one of the questions which links nicely with this idea of things not being identifiable, and Graham might want to come up against that in a bit as well. I can see him nodding, he's very small on my screen. But somebody asked when I was talking about these really, really cold things, what were these condensates? And this Pauli exclusion principle that people have been talking about means there's kind of two sets of particles. There's particles that can all be in the same quantum state, and there's particles that can't. So the fermions, the ones with these half integer spins, in the sense that Nigel has just been talking about, they can't all be in the same state. Whereas the fermionic condensate is a very clever method of taking some of these fermions who can't all be the same and getting them all to act as if they have been, by first pairing up in a particular way where they're not a bound state, but they behave correlated, so their behavior is correlated. And then this forms these the condensates. So you saw the pretty pictures at the very, very end. One other thing I would add from this slide is Richard Feynman has some really great quotes about quantum mechanics. quantum field theory, and roughly speaking, I don't have the exact phrase in front of me, is if you think you understand quantum mechanics, then you're wrong, basically. No, but I let the chair decide as to who goes next.
Can I speak on this?
Of course, go ahead.
I was surprised by this overhead when I saw it. The way I was brought up, because this was not my introduction to quantum field theory at all. I have a bit of difficulty understanding the history because the first real understanding of quantum mechanics came from Planck, who understood that light is made up of photons, and that, but then for some reason, light, which is an electromagnetic field, is made up of photons. But then quantum mechanics moved from that to trying to describe atoms and didn't really think too much about photons for a long time. But it was only, quantum mechanics was developed in the 1920s, but it was only around the 1950s that quantum field theory was developed. In quantum mechanics, we describe electric fields and magnetic fields as just sort of functions, as fields. But quantum field theory, the way I was taught it, the main point about quantum field theory was that you treat the electromagnetic fields and other fields as photons rather than as classical fields. So I thought that used to be the province entirely of particle physicists, and only relatively recently has it gone to condensed matter. So my view of quantum field theory is rather different to the one espoused on this slide. Okay, that's all I wanted to say, really.
Yes, so I'll just make a quick comment on that to link on whoever's speaking next. But I think this is one of the fantastic dichotomies of it, that the maths turns out to be the same no matter which direction you've come from it. The maths of quantizing the electromagnetic field and the maths of doing a lot of particles happens to be the same. Now, maybe Graham would like to tell us if particles or fields or any of these things are real or not, but mathematically speaking, it all is the same thing.
So certainly that the going from the maths to what's real, if the maths is basically the same depending on how you think about, like regardless of how you think about it, we can't just read off from the maths whether there are particles or there are fields, because the maths is going to come up with sort of notational variants of various kinds. So you end up having to think very carefully about what you think counts as being, as deserving a name. So if two particles are identical in the sense outlined earlier, there aren't two of them. Like if there aren't two things which are the same thing, like if they're the same thing, they aren't two. Like that's that goes back to Leibniz, that thought. So if we're thinking about things using kind of the thing concept, the concept we have for explaining what a thing is, we're running into trouble very quickly here. Similarly, if we're using the kind of concept of a field as initially we had for sort of electromagnetic radiation or magnets or whatever, clearly that's going to run into trouble when we go, but we need something that's being the particle-like thing, whatever. So a lot of philosophers, certainly Tim Maudlin, goes, look, whatever we're talking about here, it's just another kind from any of the concepts that we've been using so far. Look, we don't know how to think metaphorically in terms of it yet, but we just need to sort of get a grip on this new thing. Like when you learn another language and there's a word that just doesn't translate well into your language, you've just got to learn this new word and how it gets used. And so, and I'm not sure if I believe this, but at least a lot of the confusions here might be because we're not thinking about the history of some of the concepts enough. We're not thinking about what assumptions we brought with us. I mean, so one of my hobby horses is a lot of our misunderstandings about time might be based on Newton's theology, because he had particular views about how God was distributed through the universe. And then that kind of gets taken into the classical conception of space-time in a way that it wouldn't if you used Leibniz as your model. Like, so a lot of that kind of dead weight of metaphor that gets carried with us might create a lot of these confusions.
Can I just interject there for a second and say that there is definitely two things rather than one thing when we're talking about bosons. And I mean, the interpretation, you can give it whatever you want, but there's not just mathematically, but also an experiment. If I have two modes and I have two photons, both photons can be in either one mode or the other mode. So a mode, think of it as, for everybody in the audience, if I have two different fiber optic cables, and I know that the photons are either going in one or the other, and I send precisely two photons, I know for a fact that either the two photons went through one, the two photons went through the other, or I sent one and one, right? And these three outcomes are different, are definitely different. It's also the fact that I cannot, if two different photons went through two different positions, or they both went through one or the other, there's no way for me to tell which photon is which. And that doesn't just have profound consequences for my understanding. It even has profound consequences for physics. The fact that the universe cannot distinguish which photon is which means that the probability of this distribution for photons going through two modes is different than it is for fermions, which you could potentially distinguish, right? So if you're thinking of two photons going through two modes, what you wouldn't, if you were sending distinguishable particles, there'd be four different outcomes if you were rolling the dice. The four different outcomes are A and B both going through the first one, A and B first go through the second one, or A goes through the first and B goes through the second, or vice versa. But because you have photons and you cannot distinguish an A and B, you just know there's two photons. Really, there's three possible outcomes, and each one happens with probability a third, right? So
sure, but the lesson from this might be that photons aren't things. Whatever photons are, they're not things.
But we can't say that there's no such thing as more than one, like.
I mean, we can, because that just follows directly from them not being things.
Yeah, but then we don't understand how photon sampling works. So that's sure. No longer a useful, like, sure, I can get behind you and in the idea that science is a series of consecutive lies that we tell each other, and we haven't, and like, I'm with you up until there. What I'm saying is that the getting rid of, if you want, the fiction of there being things called bosons because we cannot distinguish them, that's not a useful move, because then there's a whole bunch of things that we used to understand but we no longer understand. And while I think that there's definite room for improvement in quantum theory, whatever comes next is going to build up on it, not more than likely. I mean,
sure, but I mean, it's hard to tell. Like, I'm very wary of getting into the business of what's going to come next. Like, I know that what's come next will obey this. You know, we've been wrong so many times before.
Sure, but
okay. I think we can stop this discussion here. I think ultimately, while we can calculate almost anything we want, for example, Paul showed us this example that we can calculate the magnetic moment of an electron using quantum field theory to a ridiculous accuracy. There are many points of that where we don't really know what we're doing. We know exactly how to calculate it, but what's going on, a lot of discussion still to be had. However, I think it's useful time to move on, because the next topic or slide follows from this one of what happens when you put a lot of particles together. Well, you get macroscopic stuff, assuming stuff exists at all. And this macroscopic stuff can be very useful. And in fact, aspects of quantum mechanics you're probably using every day of your life, as Gunnar is about to tell us.
Yes, thanks, Sam. And actually, this leads on wonderfully from this cornerstone of condensed matter physics in the 20th century, that more is different. So every time we put many atoms together, we see some new effects, and we can do surprising things with it. And actually, physicists have been very, very good at also making useful things of these. And we're showing three here, which we associate with what Carlos earlier called the first quantum revolution of technologies. And so the example here on the left is transistors, right? So this was really a completely new way to build kind of valves for electric currents out of an understanding of applying quantum physics to periodic crystals of silicon. And so as you can see, it has sparked all of the information revolution. Hard disks, which you see in the center, are very similarly rely on effects that we discovered in condensed matter physics. So here it's mostly the magnetism of the disk that we use to store the information, and then we can read it out very sensitively thanks to a surprising effect known as giant magnetoresistance. And I didn't mention the Nobel Prize for transistors, but all of these things were indeed cured by Nobel Prizes, and you see the corresponding names there. And so the final example here are superconductors, which were first discovered very early on in the 20th century, but have remained a mystery for a good 45 years before a theoretical model was found to actually explain this effect. And of course, you see again, this was worth a Nobel Prize, and actually it includes one of the only people in the history actually to have won a Nobel Prize twice. And as Sam told us the other day, it may have been because he told the King of Norway that he forgot to bring his kids the first time around, so he was going to do it again. Anyways, all of this leads on to what else can we do actually with quantum physics? And Carlos has already brought this up. And this is the second quantum revolution. And so far, we have really asked the question as to how do we best engineer individual quantum degrees of freedom that we can then manipulate, read out, and control. And some of the superconducting quantum computers that we see today, built by companies such as IBM and D-Wave systems and so on, are some early examples of that. But really, as a condensed matter physicist, we'd like to ask, what are the best materials that allow us to build such sensitive individual quantum degrees of freedom? And we already know that there's some very elegant materials where these emerge kind of spontaneously. So this is really the question that I want to throw up. Where do you see kind of the future of quantum information and quantum materials?
So Paul,
that's over to the panel.
Have a comment?
Well, I can't really talk about the future of quantum information. That's somewhat outside my expertise. The revolutions in our technologies have, to a great extent, been driven by revolutions in materials, and we use quantum. I mean, there's an army of chemists and physicists who are chemists and material scientists and physicists who are using quantum mechanics. We have many body theories within quantum mechanics, Hartree-Fock theory and density functional theory, which describe a lot of materials and the quantum properties of materials extremely well. You're talking at the moment, I'll come on to this in a moment, about rather exotic materials, but you can calculate using quantum mechanics, the electrical resistivity of copper or the specific heat of iron or whatever you like. And those theories work extremely well. However, we're now at a place in physics where there are, well, as Claire said, there are not only three types of matter. There are plasmas, there are cold atom materials, and all sorts of things. And they are testing quantum mechanics at the single particle level. And it's a very profound. There's some very profound things being learned and advances being made, particularly in marrying classical mechanics and quantum mechanics together. Where this is going in the future, I think, is that as we discover new materials and new emergent phenomena, probably the best example of an emergent phenomenon is superconductivity, whereas one electron cannot superconduct. You have to have a number of them, and it's one of the greatest insights in physics, I think, that under some circumstances, two electrons can attract one another, even though they're the same charge and you'd expect them to repel. Under some circumstances, they can attract. And that once you've got that idea, that leads to superconductivity. But it's a many particle theory that is required to understand that. And there are more and more exotic states of matter coming out and appearing, and they're going to be, on the one hand, they're going to give us greater insight into quantum mechanics, and on the other hand, the quantum physicists, the theoretical quantum physicists, should be using their knowledge and understanding to guide and push those experiments in the directions they want them to go. So I think that in the transistor, we use the quantum properties of matter. In silicon chips, we use quantum properties of silicon. But they're sort of bulk quantum properties. We're now using things like entanglement and very subtle quantum properties to drive the device to develop the devices we're trying to develop, such as quantum computers and all sorts of quantum sensors. So I can only see an acceleration in the applications of quantum mechanics via new materials and new states of matter coming in the foreseeable future.
So maybe Claire could say something next and perhaps comment on the relationship between superconductors and the fermionic condensates.
I think Sam or Gunnar, you're a much better place to do that. Remember, I'm not a physicist.
Okay, as you wish.
Thank you.
Okay, well, I mean, ultimately, superconductors are in fact fermionic condensates, but condensates of the electrons. The electrons are fermions. So a state of matter that was discovered perhaps 100 years ago and actually has technological applications is finding new aspects to it in these ultra-cold atom experiments, which will perhaps lead to new aspects which may then go round to materials again. And this is one of the fascinating circles of current research. But it's not for me to speak too much. Let's actually just ask Carlos to comment next on what's next. But you're the expert in this.
Well, I mean, I wouldn't want to contradict Graham in his statement that we shouldn't cavalierly peer into the future. I'll just say one thing, which is most people call this the second quantum revolution, or EPSRC has been calling it second generation quantum technologies. And sort of in my rebellious manner, I've been referring to them as quantum information technologies. Two reasons is because they are all really exploiting quantum information in some way or another, but also because I think it tells us a little insight. I'm convinced that this revolution that we're seeing now, that is just beginning, quantum computers are just something that are beginning now, quantum and communication technologies are just starting now. So we're just seeing the beginning of what I think the information revolution, the information age, was to the industrial age. So think of the changes that happened throughout the 20th century as we went from industrial societies into information societies. And I think that we're about to witness a similar type of revolution. And cognizant of the time, I'll leave it there.
That's brilliant. Well, thank you, Carlos. I mean, I think this has covered already many of the aspects, namely, yeah, we can learn a lot by looking at these quantum materials, and actually emergence really remains one of the most surprising effects that we see out there. So we can't really say just looking at Schrödinger's equation, although we know very well the equation that individual electrons behave according to. Once we take many of them, they're just so much new complex behavior that can appear that just surprises us. So we don't really have so much predictive power. We, to some extent, post-dict some of the effects that we observe, and superconductivity has been a very good example of that. And of course, there's topological phases and many other new states of matter that we describe now. Anyway, so we're sort of slowly working our way from the microscopic to the macroscopic. So it's therefore also my pleasure to introduce our next topic, which Nigel Mason will tell us more about. So over to you, Nigel.
Thank you very much. Yes, well, of course, as I said at the beginning, I work on the very small, and now you can't work on anything bigger than the universe. One of the great mysteries still, I think, one of the areas is how do we bring together these two things? How do we bring together relativity, which works quite well in trying to describe some aspects of the universe and the birth of the universe, with quantum mechanics, which was there, singularity and so on was there. And ultimately, these are the two big areas of science, if you like, and physics that need to be brought together. It's said that space-time and gravity must ultimately emerge from something else. And there's some fascinating theories going around at the moment to try and put these two things together. We've heard about entanglement, and some of you will have studied it in your courses. Brian Swingle at Harvard wrote a very interesting paper about a couple of years ago, which says entanglement actually, if you can understand entanglement, maybe it's entanglement, a quantum phenomena that actually creates the whole space-time continuum. So it's bringing together of these two things and understanding the universe and how these two parts brought together, I think is still one of those big challenges that modern science, physics, mathematics, and so on has. But the other aspect of space and why you're interested in quantum mechanics and why people in space are interested in quantum mechanics builds on what we just heard. We're losing a lot of quantum technologies in space. It was said earlier by Paul, we rely on all our time standards and our frequency on these optical clocks. And what better place to have optical clocks without any interference is in space. But also communications. A lot of these big communication systems, the global communication systems that are being talked about, are going to rely on quantum communications between satellites and between everything else like that. And the idea of how we do that is quite fascinating as well. But we can also build, and it was again referred to earlier on, this idea of using quantum gravity as a sensor for understanding and looking for structures and so on the Earth. So there is this new emerging area between in ESA and in NASA, European Space Agency, where we want to bring quantum technologies into space, and we want to exploit the ideas of the quantum technology in space. So that's the applied side of quantum in space, but we also have this huge problem of how do we bring together the relativity, the space-time problem, and gravity, and how does that match up to quantum? And to go back to what Graham said, is there something we're missing? Are we so conceptually wedded to things that we currently understand that we're unable to think out of the box of some brand new thing that encompasses them together? But that may be a good point for Graham to discuss.
I mean, so just on quantum gravity, a big plug for one of my favorite theoretical physicists, Faye Dowker, who I believe is currently at Imperial. It's very rare that I've come across a physicist who kind of works on time, which is what I work on, who's got such a good grasp both of the physics, in that my philosopher of physics friends go, yeah, they know what they're doing, and seems to get the philosophical issues. So she's got a really nice short paper in 2014 in which she kind of outlines the causal set theory she defends, and I can thoroughly recommend that.
Okay. Paul, maybe I think you've taught on both aspects of this in your teaching career, I'm sure, from relativity on the one hand and quantum mechanics on the other.
Yes, but I mean, this is a bit above my pay grade. I don't really know much about unifying gravitation and quantum theory. I know it's a problem, and the gravitational equations are non-linear, and the quantum mechanical equations are linear, and things like superposition. You have to have linear equations to have superposition, and things that we know exist within quantum theory. All I can see is that it's a very difficult problem. I can see that, but I can't say much about it, I'm afraid. It's just not my area.
I think this is one of those class. Sorry, Gunnar wants to say something?
No, go ahead. Yeah, please.
And I'm just moving on. So if you had something to say.
Okay. Yeah, I was going to say that, I mean, one thing that's connected is, of course, the physics of black holes.
Yeah.
So there's the well-known black hole information paradox, namely to ask, I mean, we know that if you throw some matter into a black hole, it will never come out. So what happened to the information that object carried with it? And so now we know that actually black holes don't really suck up everything forever, so they can actually very slowly evaporate. And so it's one of the big mysteries, what happened to the information in between. And I mean, again, I'm not an expert, but that is definitely one of the big questions that does relate. The size of the very small, because in the end, the information is carried by each of the individual atoms, and so on the size of the very large, because after all, black holes are some of the biggest objects out there.
Indeed.
Okay, thanks, Gunnar. That was a very nice point. And this is also shows us just how big this question is. We could do an entire 2-hour symposium about this if we wished to. But in the interest of time, let's move on to our final question that we wanted to put to all the panelists, is why should you care about quantum mechanics? And of course, maybe some of you're caring because you have to pass an exam in it in summer. But for the rest of you, why is it important that you know something? So I hope we've convinced you throughout this evening that quantum mechanics actually has aspects in your everyday life, but why should you care about this? So let's put the question first to Graham.
Cool. So, I mean, obviously the question in the back of this, why should you care about anything? I mean, that's the kind of tricky thing. Like, one of the distinctions that's worth making here is that unlike justice, pretty much anything that physics talks about will still do its thing whether or not you care about it. So justice won't happen unless you care about justice. Quantum physics will still do quantum physics even if you don't know about it. So that can't be the reason to care. But hopefully we've got an interest in understanding the world. I mean, Aristotle famously thought that the thing that characterized humans is that we had a desire to understand. We've kind of shown that it's our best theory of matter. It shows up in all these technologies, from chairs to atomic clocks to quantum computers, to whether your credit card will suddenly be unsecure next week if there's a sudden breakthrough. I sometimes lie awake worrying about that. I mean, so in terms of the why should you care thing, it's kind of just because you like understanding the world that you live in. And if you don't care about that, I'm not sure I've got anything to persuade you with.
Cool. Nigel, same question to you.
I think there's two parts of this. As a scientist, there are reasons that I want to understand what's going on around me. But I think if we think about the general public, I've been reflecting on this recently, that if we take more and more quantum technologies on board, how are the public going to refer to this? I mean, I think you've just come up with a very nice example, Graham, of the credit card. And think about the people who are worrying about the vaccine and all the social media stories and the scare stories about that. What's the media message going to be? What's the social message going to be when somebody says, oh, all these governments are running everything on quantum cryptography and hiding all your information and so on. So I think in the same way that we need to educate people about why a vaccine is good for you and you should go and have it, I think we're probably going to, if we're going to use quantum information and we're going to use quantum computing and we're going to use this as a way that actually affects people's lives by, for example, all bank transfers, I think people need to probably have an understanding of it, to nothing else, to avoid the wrong stories and the conspiracy stories. So I think that's why we need to start to think about educating people, because I think the pandemic and the vaccine, from a biological point of view, I'm seeing this increasingly perhaps as a physical view.
So Paul, you next.
I'm going to give the banal answer to this. I was a quantum physicist for 40 years. I retired recently, and we were a lot of us working, the panel working quantum mechanics, and you want the general public to pay your wages.
Very good.
They do that through their taxes. And if if you're asking them to do that, then they've got to think that what you're doing is worthwhile. So it's up to you to explain it, and if they want to know, it's up to them to listen to why quantum mechanics is a worthwhile thing. And I think we've explained that very clearly today. We've given a lot of applications that affect the general public and will affect the general public in the future. And that's why they should care about it, because they're going to be paying for it.
Claire.
So although we've given loads of examples of why we should care today, there's loads of things that we just simply didn't have the time and space, no pun intended, to talk about. And the the Physics World this month, which is the magazine for members of the Institute of Physics, is talking about some of these applications in biology. And one of the fun ones is, does the robin find out where to go using quantum mechanics, etc. So this is not the end in any sense, even though we can't answer any of those open questions. There's lots more to do in lots more areas, I think.
And finally, Carlos.
So to answer this question, I want to give a very, very short story. February of last year, I was teaching an introduction to algorithms. Course. I was teaching my students about algorithms and about runtimes of algorithms, and exponentials came into place. And while I was teaching this, the noises about the disease started coming out from China, started spreading, and people were arguing. Everybody from people online all the way up to the Prime Minister. Some saying that it's a big deal, many saying that it's not a big deal. I took one look at the R0 value for this disease. It was nearing 2.0. The R0 is, in a nutshell, for every individual that currently has the disease, how many will get it from that individual? So this R0 value being almost 2, it was clear that the growth was exponential. And so I emailed my students, first year undergraduate students, and I pointed out to the fact that the growth was exponential and that they had already studied exponential, so they knew what that meant. They immediately got it. They immediately understood what was happening, what was going to happen, even though all the way up to throughout levels of government, people were saying that it wasn't a big deal. They immediately understood the consequences. One of them emailed me back and said, "Wow, that's a grim look ahead." This is February of last year. And I say, no, well, it's not grim. It's what's going to happen unless we curb that growth somehow. And of course, now we know we didn't curb that growth. And so, and the question has come up again and again, who could have foreseen this? Anybody who could have foreseen this if they had the prerequisite education. So education saves lives. Knowledge really is power. It is a huge difference between a society who respects knowledge, respects experts, and a society that decides to, it's grown tired of its experts. Well, very soon it finds itself having no exports. So I think that's the long and short of it. We need to understand our reality, and it turns out that quantum mechanics is the best scientific theory that explains our reality as we know it, and it'll, as my colleagues have already elaborated on, it's going to have a bigger and more significant effect on our technology moving forward. And that's what I had to say about the topic.
Excellent. Thanks very much to all the panelists for their very diverse answers. I think this really tells us in how many respects we should care about quantum mechanics, and indeed the audience also cared. So it's now time to come to their questions. So the first one has come through from YouTube, and the comment was, so particles are events, not things. Does this explain the lumpy nature of quantum mechanics, i.e. its on or off behavior, no continuous measurements like 24 mph, etc. So can I throw that to the panel, and somebody can pick it up.
To start, Graham?
Well, thank you. Are particles events? Oh, that's interesting. So what is an event? I mean, so one definition of an event is just a region of filled space-time. Like So events, maybe processes might be a better category. So one of the claims that gets made for processes is, unlike things which you need to explain changes in, processes you need to explain stability in. So some of these sort of different categories just change what kind of questions you ask. So if you're thinking in event terms, you've suddenly got questions about, so we need to know how long the thing lasts, how long the event is, but we also have questions about how spread out it is. So the Second World War, classic example of an event, took place in Africa, in Asia, less so in South America, but notably in the River Plate, so we need to start sort of giving boundary conditions to this event. I'm not clear it's going to be straightforward to do that. If we're thinking of the particle-like things as events, we're going to end up this potentially collapsing into thinking of them as fields. I'm not sure.
Okay, does any other panelists want to comment on this, of why are things lumpy in quantum mechanics? I mean, I think really the short answer is we have no clue at the moment. That's the way it is. But very good question, and maybe one day we'll know. Maybe whoever asked this question will actually be the one to figure it out. Let's hope so. Good luck. The next question, we're very aware of time, so we can't ask all the questions, but we'll have a couple more. The next question we'd like to put to the panel was asked by Teodora Romanova, and she asked, if we were to lose all information or knowledge we have of physics, but still had access to the same technology and experimental capabilities of today, do you think we would come up with the same theory of quantum mechanics or something different or more advanced? Fantastic question. It's open to the panel.
I'll comment on that one. I don't think I've got an answer to it. We have the same technology and we'd have the same experiments and the same results, and we'd come up with something very similar. Quantum mechanics is a very successful theory, but we haven't got the interpretation right yet. And I think the interpretation might be very different. And in particular, with a quantity in quantum mechanics called the wave function, which is really quite central. And I'm not at all sure that would remain central. I suspect there's another quantity called the density matrix, which might become a more central quantity. So I think the theory would be the same, but our interpretation of it would not be the same.
Anyone else want a brief comment on that?
Very brief. Go ahead.
Go ahead, Carlos.
Oh, Carlos.
Well, I was just going to agree with Paul wholeheartedly. And I think history also urges us to err on that side, because many people came at it from different sides. There was a lot of different attempts to understand quantum theory, and from a mathematical theoretical point of view, we have a very good understanding of quantum theory. When Graham was earlier speaking about things that we don't understand, is we don't understand how to interpret the mathematical theoretical foundations, and that's still up for deliberation. But the theoretical underpinnings, we understand it to such a degree that it's almost incontrovertible that we would come up with, if not exactly the same formulation, something very much like it. I'm done.
Excellent. Any other comments on that question, or shall we take the next one?
So, I mean, I entirely agree with Carlos there, that I really don't want anyone to take anything I've said to suggest that we don't have a really good understanding of the math. Like that's, so one worry about the question is, if we get all of our technology and our experimental capability, you might think that we still have, by definition, most of our knowledge, because our knowledge of physics is actually largely practical, that we know how to do things. and the formalism is a kind of expression of practical knowledge. But when we think about what science is, we often think about it as knowledge of facts much more than is kind of representative. That a lot of science is actually knowledge of labs on how to do things and knowledge of communities on how to make things happen. So we would still have a lot of knowledge left. But equally in this situation, we would still have the same macroscopic metaphors that we were trying to leverage. We would still have billiard balls, and we would still have waves. I have heard it speculated that if we lived on a planet that was wetter, that land mass was less, and we all lived on like rafts on oceans, we would have just used very different metaphors to interpret this stuff, because we would have gone for stuff rather than things as the primary basis of explaining things.
Excellent. Well, thanks. So now I want to throw out one last question, which is really one of those rather big questions. And so I think it's well suited for the end of this discussion, or nearing the end of this discussion. It's from Thomas O'Sullivan, and he asks, how likely is a new theory to come along and uproot everything we think we understand? Might we eventually see a revolution akin to the breakdown of classical mechanics for quantum mechanics as well?
Will I comment on this one as well?
Please do, yeah.
It is quite possible that quantum mechanics is not the last theory we develop. However, you are sort of not quite correct, or you haven't got the full story when you say that quantum mechanics has overthrown classical mechanics. Classical mechanics is one of the best theories the world's ever known. It lasted for 400 years. And although quantum mechanics has come along and surpassed it in some ways, we still use classical mechanics because it's such a good theory. And it is possible that quantum mechanics will be overthrown and something new will come along, although it'll take an incredible intellect to do that. And there's no reason to do it at the moment because there's no terrible disagreements with experiment. But even if a new theory does come along, we'll still be using quantum mechanics because it's such a good theory. It gets so many things right, and it'll be an approximation to whatever the new theory is, as classical mechanics is an approximation in some limits to quantum mechanics. That's all I have to say about that, I think.
Yeah, excellent summary, Paul. Thank you. Other opinions on this? Seems like one for you, Graham.
I mean, so this is one of the central questions in philosophy of science, like just general philosophy of science, is what happens when new theories come along? Do they overthrow the old ones? I really like Paul's answer that actually a lot of the time they don't overthrow the old ones, that we can still make sense of knowledge. But there's lots of scientific concepts like phlogiston and ether that we're trying to think, look, how does oxygen relate to dephlogistated air? Or like, how do these concepts fit? Actually, going back to my previous answer about the practical knowledge we have, probably we will end up with a new theory just on the basis that all our old theories ended up with a new theory. So we've got good inductive evidence that this one too will change. But actually, we'll still have the practical knowledge unless we forget it. And so it won't be such a terrible overthrowing that we're unable to sort of do anything. It will just be that we've got a different set of concepts that allow us to do new things we can't currently contemplate.
Can I just add one thing, which is to say that let's not put classical mechanics under the earth yet. It did get us to the moon,
Yes.
Among other things. And similarly, quantum mechanics might not be the end all be all, but it gives us things like fMRI. So quantum computers, quantum technologies. So yes, we have to understand that science is a process. I don't know if everything in nature is a process, but science definitely is. It's a work in progress, and we have to understand it that way. But we also have to understand that theories as successful as quantum mechanics, which there really are none, but even theories that are almost as successful like classical mechanics, seldom have huge U-turns. We are likely to build upon it, we're likely to deviate it, but it's very unlikely for somebody to come and say everything you knew about quantum mechanics is wrong, right? We're much more likely to see some improvement, likely to make it work with gravity, as Nigel, Paul, and others have mentioned earlier. Like that's one of the big things, and that is likely to change one or two of relativity and quantum mechanics, both extremely successful theories. But it's very unlikely to completely throw one of them into the dustbin of history, like phlogiston or the ether. And that's what I had to say about that.
Could I just quickly comment? If you go and watch your news tonight, you're going to see all the information about the satellites going around Mars. All those trajectories, all those calculations are classical mechanics. And we have now got the opportunity to explore a brand new world, and it is classical mechanics. And classical mechanics is very important to a lot of things that we do today and works very well.
Yes, and I hope they've thought hard about which units they use so that they don't get the satellites shot into deep space. Anyway, I think we're almost around our panel. So Claire, would you like to take some final words on this one?
So, well, I think I wanted to add to it is we haven't discussed it, and I'm certainly not an expert. I'm not sure anybody is, but there are ideas out there being explored about what there is. So, you know, there's string theory, there's M theory, all of these things. There are things that we already know you can't test experimentally, and even if we threw another few $1 billion at LHC, we'd struggle. So yeah, there's lots and lots of exciting mathematics, and sometimes the mathematics is very exciting and it doesn't lead to new physical progression, but sometimes it does. So who knows, if we do this again in 20 years time, we may be talking about completely different things.
So that's, I think, a fantastic place to end. We've run a little bit over, so sorry for that, but we've covered a lot of ground. And in fact, the idea of discussing all of quantum mechanics in 2 hours was perhaps a bit optimistic, perhaps particularly from 4 different subject viewpoints. Perhaps if we'd narrowed it down to theories of the electron between March 1921 and April 1921, we'd have had more success in fitting it in 2 hours. But as you can see, there's a fantastic world out there, the quantum world. We know very well many things about it. There's also many things still to do. So challenge for Tom, you come up with our theory of quantum gravity. I'll be expecting that by Friday in your project. Thank you very much. But I think with that in mind, we've heard so much. I don't think there's any way I can sum up everything other than thanking the panel again. So thanks, Paul, Claire, Carlos, Graham, Nigel. Thanks to Gunnar, my co-host. Thanks to the audience, of course. Without you, we wouldn't have been able to justify having this discussion, which has been very interesting and entertaining for me as well. And finally, immense thanks to Holly and Joe and FISSOC for putting this on. And I think they will have the last word. So thanks all from us. Back to Holly.
Yeah.
Hi. Before I do all my thank yous to everybody, in the YouTube chat, we do have a couple of major requests for Graham's list of books on quantum mechanics and philosophy, if that's okay, just for our YouTube viewers.
Sure, one moment. I'll just get them. I sent them to somebody in the chat earlier, so I can just copy and paste. So those are the 2 books that I would recommend if you're interested in the philosophical issues.
Okay, I will copy that into the YouTube chat, but that is Tim Maudlin, The Philosophy of Physics, Quantum Theory, and David Z. Albert, Quantum Mechanics and Experience. So they're also in the YouTube chat. So what I was going to say was I want to thank all the academics so much for taking so much of their free time to do this. I think it ended up amazing. I found it really interesting. It was just a really, really good event, and our most successful event all year, and one of the more successful from my 2 years doing PhysOc stuff. So that's really cool. And I also wanted to thank everybody who came to watch. We actually at one point had like 70 people watching at once over the YouTube and the Zoom. So that was just amazing. That really blew me away. Yep. Thank you so much, everybody. I'm so happy. Yeah.
Thank you for organising it, Holly. I really enjoyed it.
Thank you very much, Holly.
Indeed, yeah, I can mirror that. Very well put together. So thank you for that.
Actually, let's have a round of applause, I think.
Okay, I'm going to end our